Okay. What'd you get for the first one? 0. How do you know that? It's negative what cosine, and you plugged it in? Okay, how else could you have done this? Well, kind of. Thinking through this, from negative pi to pi, we see that these are going to cancel. That's going to happen anytime you have an odd function. How'd you do the second one? How are we going to do the second one? No, you cannot break it apart. You can if the numerator is being added, but not if the addition is in the denominator. Okay, the only way we're going to be able to solve this is if it's odd. How can we tell if something is odd? What thing? It's f of negative x equals negative f of x. So we need to plug in negative x and see if we get this, where the whole thing becomes negative. Does it? It does, right? Because we see that it's not going to change down here. It's only going to change up here. All right, so this is also equal to 0. So be careful about this. It happens when there's odd functions, but over a symmetrical interval. Okay, what about the last one? Okay, so this is why some certain people that we love say that integrals are antiderivatives. It's not an antiderivative, but when we have an indefinite integral, meaning we don't have bounds, the best we can do is write the antiderivative. So that's what we do. No, they're not. Okay, perfect. Okay, I don't know if any of you read the book yesterday, but if you did read the book, you would notice that there's actually not anything in your book called the evaluation theorem. It's called the fundamental theorem of calculus part 2 or something like that. So yeah, it's a little bit odd. What? What'd you say? Oh. Okay. The fundamental theorem of calculus. Okay, so let's look at this. It's fundamental. It must be pretty important, yeah? This should say 1, not x. Okay, let g of x be equal to the integral from 1 to x of 4t plus 2 dt. Now this is interesting because we have an integral, we have a definite integral, but the top limit isn't defined. It's the variable, actually, in the equation. So, kind of weird. All right, let's see what happens at several inputs. So let's find g of 3. How would we go about finding g of 3? Be the integral from 1 to 3 of 4t plus 2 dt. And let's just do the scratch work over here so we can keep referring back. The integral would be 4t squared over 2 or 2t squared plus 2t from whatever values. So from 1 to 3 here. What's your question? Well, because you have to. This inside of here is the area of the rectangle. So if you leave this part off, then you just have a height, and I don't really know what that means. I'm just adding up a bunch of heights. You have to have the area, remember Riemann sums and okay, yeah. If you leave it off, it's like crucial. It's pretty important. Okay, So 2t squared plus 2t from 1 to 3, if I plug in 3, I'm going to get what? 18 plus, okay. Y'all are way faster than I am. Okay, 20. Okay, what about g of 1? This one's not too hard. What about g of 1? The integral from 1 to 1 is 0. Yeah. Did you say you said that? Awesome. Okay, what about g of 0? Okay, so if we plug it, okay, first of all, we have this issue. And we haven't talked much about this, but going from an upper bound to a lower bound. Yes. We can say that's equal to negative the right way, 0 to 1. We think about integrating from left to right. This would be integrating from right to left, which is going to force the area to be negative. If it's above the axis or positive if it's below. Okay, so g of 0 was what? Did anyone say? Are you sure? Are we just trusting your word? What about g of x? Well, it would be the integral from 1 to x of 4t plus 2 dt, which we know is going to be 2t squared plus 2t from 1 to x, which is what? 2x squared plus 2x minus 4. All right, so we actually found g of x. Now, when we think about this idea of functions being defined by integrals, because that's what we had in the beginning, right? G of x. I could have written g of x like this, but I didn't. I wrote it like this. This is how we started. So when we think about functions defined by integrals, we're going to think about them as accumulation functions. We're starting at 1, and I'm just going to start accumulating area until I get to whatever place I want. Okay, so I'm just going to keep accumulating area. If I go this way, I'm still accumulating area, just in the opposite direction. So here I'm accumulating negative area, and then I start accumulating positive area. You see? When it switches sign. Okay, so we're going to think about this as an accumulation function. All right. What would happen if I asked you about g prime? What is g prime? Yes. What is it more specifically? 4x plus 2. Does that look familiar at all? Why is that crazy? Because it was 4t plus 2. So what just happened? No. What just happened? Seriously. Calculus. Great calculus answer. What just happened? Like a big deal just happened. We integrated something and then we differentiated what we got and we got what we started with. What does that mean? What? Yes! Integration and derivatives are inverse processes. Dr. Shear makes me so happy. No. You can't. Okay, integration, it's kind of like saying addition and subtraction are like inverse processes. They're not the same thing. They're inverse processes. So integration and differentiation are inverse processes, which is what we find. Actually, this was a really big deal, y'all. A really big deal. Because for years, like hundreds of them, there was a group of people working on differential calculus. And they were like all by themselves, working on differential calculus. And there was this other group of people that were working on integral calculus. And they were like sort of separately doing their thing. Like you had Isaac Newton over here, and Archimedes and all these people working on differential calculus. And you had these people like Riemann and Leibniz and all these people working on integral calculus. Okay, then somebody whom we don't actually know because they claim that they all did it. So someone decided that, wait a second, these things are actually connected. And the way they're connected is the fundamental theorem of calculus. Now, we just learned it in like 10 minutes. It was like no big deal. But they studied it for years before they ever made the connection. So actually we just stumbled upon something that was pretty profound. Even though you are like, okay. So integral, so this is really interesting because integration, remember, is the area under the curve. Derivatives are slopes of tangent lines. And these two ideas are seemingly very unrelated, right? Why would the area under the curve be related at all to the slope of the tangent line? It doesn't, they're completely different ideas, but they're actually inverse processes. So pretty cool, pretty big step in calculus. Okay, so we have the fundamental theorem of calculus. If g of x equals the integral from a to x of f of t dt, then g prime of x is equal to f of x. We're actually going to talk about that. So hang on a second. Okay, the reason there's two different variables, we have g of x and we have f of t. The actual variable in the function is the x. That's the actual variable. F of t is a function, but it's not changing. It's the same function no matter what x is. Does that make sense? So it's acting as a constant. It's acting as something that doesn't change. Well, functions need variables. We just shorthand them and say f. But the big thing to know is that you absolutely could not say f of x dx. Because that would mean that like the function's changing and the upper bound is changing, and I don't even know what that means. Okay, so we have to have a different variable. Okay, so let's look at, we're going to go over the proof and stuff maybe on Monday. I'm trying to hurry for sake of time. Let's try one more problem. I'll actually just put it up here. Okay, here's our function. This is actually f of t. Right there. Okay, those are f of t. As h of x is equal to the integral from 0 to x of f of t dt, and I want to know what is h of 2. So I'm looking for the integral from 0 to 2, which is what? Here? It's 1, yes. Okay, what is h of 0? Oh, I wrote it. Why? What is h of 4? Also 0. Here's the question. Are there any local maxes or local minimums? So we're going to think about this two ways. The first way is going to be as an accumulation function. So let's see. We start at 0 and we're going to accumulate area. We're accumulating. What happens here? We start taking away, right? Yes. Okay, so we see that there's a max here. Okay, then we start taking area away, taking away. What happens here? Minimum. And we start adding area again. Now think about this. We thought it through being an accumulation function, but what else do we know from the fun charts? Where is the maximum going to happen? Where the derivative changes from positive to negative. Did that happen here? No. This is f of t. So I'm talking about h of x. What is h prime of x? according to the fundamental theorem, f of x. So this is the derivative graph. Imagine that! Both things match up. This is pretty cool, huh? No, you can't say. Okay, so we see here that if we think through this either way, if we think through it as an accumulation function, we can find the maximums and minimums. If we think through it as, well, to find the max, we need to figure out where the derivative changes from positive to negative. We have that also. Do you see? That's pretty cool, huh? Do you think that's pretty cool? I think it's pretty cool. We've discovered some really awesome things. Okay, perfect. Here's a great question. What's the absolute minimum? Okay, before you jump to conclusions, let's think this through. I want to know if this is the absolute minimum. Now, is this an open interval or a closed interval? Closed. So that means that the minimum could happen at the endpoint or at the critical number. So let's see. If we start here, how much area have I accumulated? None. Okay, so that's 0. And then I see that I accumulate, I take away. So this could possibly be the absolute minimum, but how much area have I accumulated there? Also 0. What's the absolute minimum? 0. What's the lowest y value? The y value is the area. So starting at 0, I go bigger, 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 smaller, smaller, smaller to 0, and the bigger, bigger. What's the smallest area? 0. Okay, if I'm looking for absolute maximum, same thing. If I accumulate area to here, how much have I accumulated? 1. So this is a possibility, and this is a possibility. So this would be 1. Then if I accumulate all the way to 5, how much do I have? A half. So what's the absolute max? 1. See how all this is connected? It is crazy. It's awesome. Crazy awesome is what it is. Okay. I thought I had another sheet. You cannot play.